Okay, let's talk about 3D. Fluorescent has its own story, and 3D also has its own story too. When I conducted a user survey in 2018, that year Olympus was actively promoting 3D technology. I believe it was our local maternal and child health hospital where Dr. Chen, head of gynecologic department, told me I cannot get used to the 3D. It makes me dizzy. And I also talked to another doctor, and he told me the same thing. One day, I found PhD students just sit behind him, and I just asked her, "How have you used the 3D before? How do you think of it?" And she replied, "I don't get dizzy, and it's easy for us to use." Now everyone is starting to use 3D. I was thinking that after 6 years, a large number of young doctors who play games intentionally are actively pushing the popularization of 3D technology. Of course, it may also be related to the promotion for robotic surgery. But we cannot ignore the fact that there are challenges in promoting 3D, such as dizziness, adaptation time, and even dislike of wearing 3D glasses. These problems are actually all related to visual comfort. There are many factors that affect the comfort for 3D systems, such as left and right channel image consistency and depth perception, rotation, and 3D display. We'll talk about this one by one. Let's start with the comfort factor of 3D endoscope, left and right channel image consistency. The main involved color inconsistent between the left and right channel. For example, if the left and right eyes are two separate optical passes, and if only the left channel white balance was done, however, the white balance may be not suitable for the right channel, right? In this case, the user would feel uncomfortable. What is the right way? UWB calibration for both left and right sensor to make sure the two channels color is almost the same. Similarly, there are requirements for consistency in parameters in such as brightness, contrast, vertical and horizontal consistency of the left and right channel images, etc. Ensuring consistency in the basic image performance of the left and right channel is a fundamental requirement for achieving 3D comfort. The second key fact is the depth perception. This depth perception is also difficult to explain to surgeons why it feels comfortable. Our team then set up an evaluation method and conducted intensive experiments to find that depth perception can be presented objectively through the depth perception evaluation curve of our first and second generation 3D product. We can see that the stable, the 3D, the stronger the depth perception, and the more positive reviews we get. Of course, there is limits for the slope value. It cannot be infinite, as the slope will be limited by physical space. Also, it needs to be in line with human eye habits. I have to say this is a good method to evaluate depth perception. When surgeon use current 3D product, he cares the rotation performance very much. Why? When 3D endoscope rotates, the horizon in the picture cannot tilt. It's like driving a car. We see the road ahead of us in our eye, but in the map navigation, our absolute position may be below our previous position. But we cannot set the map navigation to move downwards. This is not consistent with our current habit of seeing things with our eyes. So, the navigation will rotate the direction to keep it consistent with what we see in front of us. The requirement for 3D products for surgeons is similar to the example in map navigation. No matter what direction the 3D endoscope is rotated, the horizon in the picture must consist with doctor's understanding habits. I think doctor was aiming for something like this. No matter how endoscope rotates, the bamboos will always be pointing upwards. What are the challenges in making this happen? Because the 3D we made is an electronic 3D endoscope solution. Electronic 3D endoscope solutions are different from the optical 3D endoscope. With optical ones, when you turn it, the sensor is at the hand end, so the horizon in the image doesn't have the possibility being skewed. But with electronic 3D, the sensor is at the front of the induction part. When the 3D titters, the image captured by the sensor also titters, and the view we see changes. At this point, a series of coordinate calculation, angle correction, stitchings, and image process are needed on the CCU. This presents a challenge for algorithm. A good algorithm can ensure both real-time performance and image quality. A poor rotation algorithm can significantly degrade the 3D experience. The comfort of 3D system is also greatly affected by 3D display. After a lot of effort was put into capturing and processing the signal, it's important that the final stage accurately display the image. Otherwise, all the effort could be in vain. What facts affect the 3D effect of 3D display? First, signal interference can be a problem. It can make it difficult to synthesize the 3D image, which can be quite uncomfortable. Then, the brightness of 3D display has also a significant impact. Because 3D glasses are required, the glasses will reduce the brightness of the display. And if the display's brightness is not sufficient, the doctor may feel that the image is not bright and may feel tired and uncomfortable. Additionally, facts such as color, viewing angle, and the stability can also affect the 3D experience. After aligning this, it's clear that 3D comfort is a system problem. It should be solved from the top level system design. HIKIMAGING can provide a full chain solution for 3D image. From 3D endoscope, net source, CCU, we can provide the total solution. Both white light and fluorescent 3D solutions are available. Let's start with the white light 3D, which we launched last year with the EC54. Actually, there is a big design change for EC54. That is the dimension of insertion part changed from the previous 11 mm to 10.4 mm. For this 0.6 size, it actually took our team 8 months to complete the verification. There is also a particular algorithm optimization based on ISP version 2. Because of this update, the critical performance are very close to styles. For example, resolution and depth perception, you can see in this chart. This is the story of EC54 White Light 3D. Last year, I was saying that 4K 3D was underway, but it's not easy to realize real 4K 3D, no matter optical 3D or electronic 3D solution, as the physical limits of lens. We finally only select a 8 million pixel sensor that meets requirement of pixels and CIA. The sensor used in EC55 has similar pixel size to that of EC54, but with more pixels. The horizon and vertical resolution in test mode will look better. Note that this is in test mode, where the image is not full screen, but the sensor is full utilized. If used in actual clinical setting, electronic zoom would need to be used to fill the screen. After scanning, the actual results would be similar to those of the EC54. We want to be honest about this data just for your reference. So the resolution here is higher, and all the data is from the test mode. Of course, you can also do a surgery in this test mode. We have tested it, and the field of view will be bigger and clearer than EC54. But we don't know how many surgeons would be willing to operate in this non-full screen mode. It's needed to experience the mode by yourself and give us feedback. For EC55, we are labeling it as a new 3D white light product, not a 3D 4K white light. Okay, let's talk about 3D fluorescent product. The 3D fluorescent you saw at launch event last year was just debugged out the day before the event. And at that time, the demo was static and could not be moved. After the event, we thought we could quickly move to the next stage, but it's disappointed a lot of people we delayed. Basically, we completely rebuilt all the algorithm for 3D fluorescent system, including light source control algorithm and the 3D fluorescent algorithm. Although it took a bit longer, it's worth it, as it makes it much faster to produce 3D fluorescent products in the future. Yes, we have the capability to do new 3D fluorescent faster. First, take a look at the principle of 3D fluorescent electronic endoscope. Here is a joke for you. One of our technical service engineers was first to use 3D fluorescent endoscope, and he was shocked. Why? He called the head office engineer and said, "Is our light source broken? It's flashing on and off. Why doesn't it stay like a 2D light source?" The head office engineering calmly told him that's normal. After learning about this, we quickly conducted in-house training. Today, we'll take this opportunity to show you the principle in a video, because our 3D fluorescence is placed at the front of the induction port in a space of 10.4 millimeter. It's difficult to place two sensors, right? The two sensors can only be used to connect white light and the fluorescent data. So when the fluorescent mode is on, the 3D endoscope needs to cooperate with the light source to collect the data. In one frame, is connect white light, and in next frame is connect fluorescence. The light source flashing line is then a stage of alternating white light and fluorescent excitation light. The collected data is then processed through algorithm to create a 3D fluorescent image. This is how 3D fluorescent images are produced. The flickering of the light source inside cavity will not be noticed by the surgeons. Yeah. The surgeon's eyes are always fixed on the screen, so while inside the abdomen, no one will notice the light source flaking. This principle is mainly intended for technical support staff to understand. Because of time division multiplexing, the 3D fluorescent mode will only flicker when turned on. And if it is only in white night mode, it will be the same as the previous white night mode. The 3D fluorescence issue is similar to the 2D. Fortunately, the experience we have accumulated in 2D fluorescence can also be applied to 3D. As we mentioned earlier, we optimized both the optical and algorithm part to make 2D fluorescent better, and we applied the same strategy to 3D fluorescent. For example, we designed 3D lens with reduced train night, better lens filterings, and algorithm gain control strategies, as well as the support of ISP version 2 algorithm, which has resulted in positive feedback from a local clinical trial for our 3D fluorescent product. We are also very sincerely launched 2 series of 3D fluorescent products today. One is EC59 and the other is EC15A. Let's talk about EC59 first. The main feature of the Intel system is shown in this diagram. About the light source, we have 2 options. One is a laser solution, and the other is an LED solution. Laser products have a regulatory requirement both in China and internationally. The challenge in the registration process for laser light source may be greater. LED products, on the other hand, are generally easy to register aboard. The white light flexing of the 2 light sources is basically the same, but the amplitude flex of LED is much low, so it is generally safe. The difference between EC50A and EC59 is similar to difference between EC55 and EC54, which is that sensors and lens have been adjusted. The resolution of the sensor is 8 million pixels, and the vertical resolution indicator will be better in test mode. If we bid on a project and need to meet specific performance criteria, this would be an advantage. In terms of actual clinical effect, EC59 and EC15A perform similarly when used at full screen magnification. Next, I want to especially talk about 3D solution for surgical robots. You may think that 3D for surgical robotic and 3D laparoscope are the same thing. We used to think so too, but we naturally realized that there is actually different. The first and the most important requirement for the surgical robotics 3D is low latency. Why is low latency so important? Let's take a look at the usage scenario and the link of a surgical robot. First, let's take a look at the local operating room scenario. In this Intel scenario, there are several major delay blocks from data connection to processing to display on the main control panel. T1 is delay of data connection. T2 is the delay of image processing. T3 is the delay of main control panel interactor integration. And T4 is the delay of display. When these 4 delay blocks are added together, it's total delay that the operating room user can experience. Many domestic and foreigner experts can reach a consensus to this scenario. That is, the total delay is less than 100 milliseconds, which is acceptable. Of course, the shorter, the better, so the surgeon's experience will be better. Let's take a close look at the delay path in remote surgery scenario. This process is more complex, so I just simplified it and assume that the delay paths are divided into the following parts. Tier 1 is the delay in local team capture and processing the video. Tier 2 is the delay in coding and uploading. Tier 3 is the delay in remote transmission. Tier 4 is the delay in download and decoding. And Tier 5 is display delay in remote control panel. These 5 delay paths make up the delay from the local end to the remote end. There are so many robot manufacturers who are conducting remote surgery experiments at home and abroad. The expert can now reach a preliminary consensus that the total delay of 100 to 300 milliseconds is acceptable. From the above scenario, it's clear that if we want the overall system latency to be good, we need to try to control the latency at each stage. Since we provide solution from data connection, processing, and display, the system latency time will vary depending on the way we implement ISP processing. Our system latency is between 40 to 60 milliseconds. How did we get the 40 milliseconds? We performed row by row or frame to frame parallel processing under the condition of low cache and the reductant protection mechanism. The data connection and the processing time can be around 20 milliseconds. The display has response time about 18 milliseconds, so we can control the total one around 14 milliseconds. If we add some cache or reductant protection measure in the image processing stage and lead to read and write DDR, it may add another 20 milliseconds or so. Most robot manufacturers want us to provide a version, a software version, with 14 millisecond latency. Of course, we can provide this kind of software version. However, we will also inform them the corresponding risks. The second special requirement for surgical robots is the shape. The shape including length and other specific shape requirement for the insertion part. The design of a mechanical arm for each company is different, so there are different requirements for the length of the insertion part. Because our 3D solution, electronic 3D endoscope solution, the length is not a problem. Unlike optical lens, where the lens and the light path design are completely different. It's not easy to achieve. This is for optical solution. But we currently can offer insertion part solution ranging from 300 to 600 millimeters. There are some single-port surgeries that require flexible 3D insertion device, and we will also provide corresponding 3D image solutions according to their customers' requirement. We have set up a prototype display area. We could appreciate your feedback. The third spatial requirement is fluorescence. Surgical robots typically perform complex procedures, and many of them require fluorescence. The current fluorescence in DaVinci system is still fly mode. It seems that the fluorescence hasn't changed much in DaVinci 5 yet. The kernel of fluorescence fusion for the surgical robot will be better than the 3D fluorescent laparoscope because the mechanical arm is more stable and does not produce frame-to-frame error due to handshaking. At that time, the distance from 3D endoscope to the target is predictable. Therefore, the fluorescent gate can be specially optimized to achieve the best fluorescent results. ICG image algorithm for robotic 3D can be different from 3D laparoscope. This is the summary of our robotic 3D solution. I didn't share the 3D image effect as it's not easy to show for the screen's limit, but we actually mentioned it at last year's launch event. Any algorithm in our 2D system will be integrated to our 3D product. For real experience, I suggest you apply the samples for test and give us valuable feedback. Well, back to this question again. Is that all? Are you satisfied? No, we are not satisfied with the current physical limitation of 3D and want to do better 3D. Meanwhile, in robotics 3D, there is more data in more dimensions to support the development of new 3D applications, which are the direction for the 3D moving forwards. To take 3D imaging and the function to next level, we need a new platform. To stay tuned for our new 3D solution in 2025. Next, it's time for the launch of our 4K 3D display mode. We started working on this product since Q3 of 2022. And there were so many obstacles along the way, and I won't go into the detail here, but finally we made it. Let's start with the key process in 3D, which is the lamination process. This process is very precise and requires pixel-level alignment. If there is crosstalk, the entire 3D effect will be difficult to guarantee. After the decline of 3D TV, the manufacture of this polarization film process has basically disappeared. Now, there is a demand in medical field, and some upstream company has joined in. We hope that excellent upstream company will join in to make 3D ecosystem healthier. Next is the panel. For a display monitor, the panel is always very important. Our plain color filters are 14% thinner than 2D panel filters, which effectively reduce the distance from the polarizing film to the pixel point, allowing to reduce crosstalk, thereby improving the view angle. With the experience of a 2D display, we have also carried over the good code from previous color gamma and color consistence calibration to ensure that the color style of the 3D screen is either unified with our 2D display module. Then, there is the full chain anti-interference design. The 3D display has undergone the longest anti-interference testing of any product we developed in the past 2 years. Before the polarizing film arrived, we started testing the EMC performance yet. We also built on our experience with 2D display to implement high-level hardware protection and software anti-interference design. Now, let's take a look at the real-world data. On the left is our monitor, and on the right is that of other company. We tested the ESD of the display. You can see the difference between these two monitors. In this case, I still strongly recommend you choosing a better monitor. I was seeing this for many years. System problems should be solved systematically. Blackouts or flickering during surgery will give user a bad experience. A good monitor is not the one that the manufacturer is well known. There are still many brands that are well known but did not spend time on anti-interference. In fact, it's not difficult. As long as you put your heart into it, you can definitely do it well. We are the same. Our focus in future will be to ensure the consistency of anti-interference performance for every monitor, which is our quality control requirement. This is a summary of the key specification of our display. Here are some updates to our mixed product line. We mainly talked about the science of colors and the 3D. Hope these updates do good to you. As we continue to expand our product line, we are seeing increased demand for our solution. However, HIKIMAGING, we have always approached product development with a clear strategy. Build a platform first and then use the platform to incubate new products. Each platform has its own mission and positioning. For example, our Mic 3 was designed to break through the limitation of 2D 4K, while Mic 5 is focused on supporting 4K, ICG, 3D, and AI version 1. Based on their different positions, the platform architecture is different, with some features 4 cores and others 8 cores. We originally thought we could move directly to Mic 7, but in Code 1, our team surprised me by presenting a new platform they have developed. I named it Mic 6. So, what is the positioning of Mic 6? Under the leadership of our domestic industry leader, we all went all in one overnight. That's right. A multifunctional device that requires a single platform to support multi endoscopes input. But our previous Mic 5 were capable of handling multifunctionally at the core level. Still has one input interface, which was actually many processing cores and one input. It was very inconvenient for us to demonstrate this, as we had to unplug one input and plug in another. But ultrasound products also require so many support for multi-probes with a row of probe ports on the cart directly connected to various probes. The doctors can simply switch to the desired probe by pressing a button. How convenient! Our camera system could also be like this. If we want to achieve multi-modal, multi-input, we need strong input access and processing capability. Additionally, we have more and more clients with higher requirements for customization who need our platform to have more open data exchange architecture, unlike the current Mic 5, which is not very friendly or compatible. These 2 points are the mission of Mic 6. This is our Mic 6 platform. Its processing power is basically the same as that of Mic 5. You can see the parameters on the right, which are basically the same as those of Mic 5. But on the left, that is what Mic 6 can do. First, it supports sensor input. With a maximum of 3 physical channels, each channel's input capability can be 2D or 3D. The status information of each channel has a control command that can be freely switched between channel while the UI without powering off. The platform provides a rich interactive network that can interact with the Windows system, Linux, Android, and RTOS system hardware both. The peripheral input also supports PICE input no matter wired or wireless, and the rich peripherals device communication interface is also supported. The Mic 6 based 3-input all-in-one CPU will be released in 2025. It is a great option for those who want a more compact and cost-effective solution.